Now we turn to the Gordon Prize lecture. It's time, this is the 2014 Gordon Prize for Engineering Education Recipients Lecture. This prize recognizes innovative engineering modalities in curricular designs, teaching methods, technology-enabled learning that strengthens students' capabilities and inspire them to become superior engineering leaders. The Gordon Prize is named in honor of NAE member Bernard M. Gordon, former chairman of Neurologica Corporation. It was endowed by a generous gift from the Gordon Foundation. The $500 annual prize is equally shared by the recipients and the recipients' university to support the continued development of the award-winning program. In May of this year, the NAE proudly awarded the 11th Bernard M. Gordon Prize for Innovation and Engineering Technology Education to Dartmouth College educators John Collier, Robert Graves, Joseph Helble, and Charles Hutchinson for creating an integrated program in engineering innovation from undergraduate through doctorate to prepare students for engineering leadership. The winning Dartmouth Engineering Entrepreneurship Program is a multidisciplinary education model that integrates entrepreneurship and leadership training into all aspects of its curriculum. Upon entering the program, students are immersed in a liberal arts and interdisciplinary program-based teamwork activities. At the master's level, students partake in a business curriculum through a partnership with the university's business school. The program helps prepare students for technology leadership positions by allowing them to take management, finance, and marketing courses. The PhD Innovation Program trains students to develop entrepreneurial skills while enabling them to pursue independent research and developing commercialization methods for their discoveries. John Collier, Robert Graves, Joseph Helble, and Charles Hutchinson have all played an integral part in the creation of this innovative educational paradigm, from its initial launch to include project-based learning and engineering curriculum, to establishing the intent to create engineering entrepreneurs and managers who will solve our world's great challenges. Drs. Helble and Hutchinson are here with us today on behalf of all of the 2014 Gordon Prize winners. I do ask Dr. Helble to come to the podium and present the Gordon Prize lecture. And Dr. Hutchinson will stand to acknowledge us and in the welcome. Thank you very much.
Thank you, Dan, and thank you everyone for joining us here today. Now, I have to point out that Dan indicated that the Gordons were extraordinarily generous in creating this prize, which resulted in Dartmouth receiving $500. It was actually $500,000. We would have been honored to receive a $500 award, but the 3 extra zeros make it that much nicer and enable us to do that much more. So the Gordons, if you're here today, thank you so much, and thank you to the NAE for selecting us for this honor this year. We're deeply appreciative. So I'd like to spend the next half an hour or so telling you a bit about our engineering entrepreneurship programs, our efforts in entrepreneurship and enterprise education that span from undergraduate elements that Dan mentioned all the way up to a relatively new program in the PhD. This is, by the way, a picture of some of the buildings of our School of Engineering on a beautiful fall day in Hanover, New Hampshire. I want you all to know that the weather is like this in Hanover, New Hampshire until mid-February at least. We get snow for a day or two, and then it's springtime. Any of you who have children who are prospective Dartmouth students, please repeat that lie. The context for our programs is really a decade of discussion that originated with reports written or contributed to by many of the individuals here in this room. A decade ago, you may remember there was a considerable amount of dialogue about a national need in this country for STEM education for global competitiveness. We heard about rising levels of engineering enrollments around the world. We saw that enrollments in the US were steady or declining, and there was considerable hand-wringing over the state of federal funding to support the engineering R&D enterprise. This led to the America Competes Act, which set as a goal significant increases in funding in the physical sciences and engineering, and had the nation focus in a way that hadn't happened before on the importance of providing support to engineering, to the engineering enterprise, to engineering R&D. Less noticed in many of these reports, they also cited the need for transformation of undergraduate education and better translation for invention out of laboratories to, and I quote, ensure that the United States remains the premier place in the world for innovation, for technology innovation. These reports set the context and provide the background for programs in engineering entrepreneurship, engineering technology leadership that we've seen develop over the past decade or so, and they also provide context for much of what I'm going to speak about related to the Dartmouth effort today. So first, let me take a few minutes just to give you a bit of a background on engineering at Dartmouth. So Dartmouth is an old university. Dartmouth was established in 1769. It is the last of the colonial colleges in the United States. And the School of Engineering was founded just about 100 years later, in 1867, where we received an endowment from Sylvanus Thayer, who's considered the father of West Point, and we named a board of overseers. It took us 4 years to search for candidates and hire the first dean and faculty member, and we began teaching classes in 1871. We were established, the Thayer School of Engineering at Dartmouth, as a professional school, which was fairly unusual in its day. In fact, it's fairly unusual even today. From the beginning, there existed the idea that a well-rounded engineer must first complete a liberal arts education before he or she could take engineering studies building on that liberal arts foundation. From the beginning, there was the notion that engineering existed to serve society and address broader problems in the world. Our current model is an engineering sciences model. We have no academic departments, no engineering departments within the School of Engineering. Although we were founded as a school of civil engineering and later added electrical and mechanical tracks within engineering, in the early 1960s, we did away with these completely, became a single systems-based integrated undergraduate program in engineering. Students pursue concentrations to learn the fundamentals in the disciplines such as mechanical, electrical, biomedical, and so on, but their degree is an engineering sciences degree that integrates across the curriculums. From the beginning, in this engineering systems approach, we've also had a strong emphasis on open-ended design and innovation, as I'll show you in a minute. We are, at this point in time, one of the largest interdisciplinary programs of engineering in the United States, and I believe we may be the only one that requires you to earn the Bachelor of Arts degree in engineering before you can earn the ABET accredited Bachelor of Science or a Dartmouth Bachelor of Engineering degree. So we proudly advertise ourselves to prospective students as a 5-year program to build the foundations, learn the liberal arts, to provide context and understanding of the world that your engineering tools are going to enable you to address and improve. Our focus has been outward from the beginning. As I said, this is something that is near and dear to every engineering student at Dartmouth. These are words attributed to our founder, Sylvanus Thayer, from the 1860s, and they are quite literally carved in stone in the outside of our buildings to prepare the most capable and faithful for the most responsible positions in the most difficult service. From the beginning, we have taught our students that engineering is about looking outside and changing the world. Now, our programs in engineering, innovation, and entrepreneurship actually get their foundation through two individuals that some of you may know. These are both former Dartmouth faculty members who were members of the National Academy. Myron Tribus, who was the Dean of Engineering from 1961 to 1969, introduced the foundation of open-ended design and project work into our undergraduate curriculum. He felt that at that time, engineering education, certainly as it was practiced at Dartmouth, but as it was practiced at many, many institutions, was very textbook driven and deferred the fun. Am I too far from the microphone? Can you hear me back there? I've been corralled. As a second-generation Italian-American, it is very difficult for me to stand still at a podium and not move around and wave my hands, but I'll try. So Myron Tribus, the Dean of Engineering from 1961 to 1969, felt that we needed a more dynamic approach to engineering education that allowed students to experience project-based learning much earlier in their education, as earlier as their first or second year. Now it's second nature for many of us, but this was a radical departure in the early 1960s. He soon hired Bob Dean as a faculty member in the early 1960s, and Bob oversaw the development of the first foundational course with a goal of producing engineers who could in fact stand with one foot in each world, meaning the worlds of engineering and the worlds of business, who could be technology leaders, who could be technology entrepreneurs. This foundation led to a significant enhancement of undergraduate engineering project-based courses that teach elements of entrepreneurship and leadership skill development, led subsequently to the development of a master's level course, a master's level degree program in engineering management, which my colleague Charles Hutchinson was instrumental in launching, and finally led to the development of a PhD program focused on technology, innovation, and entrepreneurship in the last decade. And it is these elements together, building on the foundational work of Myron Tribus and Bob Dean in the 1960s, that led to the Dartmouth Engineering Entrepreneurship Program and its recognition by the NAE. So in talking about this in a little bit of detail, what I'd like to do is break it apart into some of the different elements to give you a sense of our approach to addressing entrepreneurship and leadership development in each of these areas. So first, of course, I'll start with the undergraduate program, which is the Bachelor of Arts program in engineering, as well as the ABET accredited, the professionally accredited Bachelor of Engineering degree program. The first course that undergraduate students experience at Dartmouth in engineering is a course that has a fairly prosaic title of Introduction to Engineering. It's actually known mostly as the course number Engines 21. We're an engineering school. I've asked in the decade I've been there whether we couldn't come up with something a little more creative and dynamic to describe the course, given the experience that it provides, but it's been for many decades known simply as Introduction to Engineering. The course is an open-ended, design-based project course, not addressing a problem that the professor puts on the table, but addressing a problem in an area that the students themselves care about. The idea is to help students express creativity and understand the creativity inherent in engineering from the get-go, from the very beginning, and carry that with them as motivation as they get into some of the more difficult mathematically and physically and chemically oriented classes that will carry through the middle part of their education. So the professors choose nothing more than a theme, providing guidance yet significant latitude. The students themselves choose the problem. Students are then told to brainstorm possible approaches to solving this problem, sketch it out, refine their ideas, brainstorm some more, develop a prototype, refine that some more, enhance the prototype, design their solution, build it, test it, do a patent search, do a market analysis, do an economic and cost analysis. And what they do, rather than writing reports for a professor who's overseeing the class, is present repeatedly to a review board of practicing engineers who are sitting there critiquing not just their presentation, but their technical ideas. It's a course in designing, testing, writing, speaking, and inventing, and they do this all in 10 weeks. This course, its Introduction to Engineering, has been described on Dartmouth's campus as truly an introduction to entrepreneurship. We've reached the point with increasing interest in engineering that this foundational course is now offered 3 times a year with enrollments approaching 200 per year. To some of you from large public universities, that may not sound like much, but Dartmouth has an undergraduate student body of about 1,000 per class, so 20% of the Dartmouth student body is taking that class. This is in a liberal arts university. 20% of these students or more are non-majors who are taking this class simply to get the engineering experience, because this is the place you go on campus to express your creative side, express your creative energies. The themes, as I mentioned, are intentionally broad to help facilitate these opportunities. Over the past 2 years, students have been given challenges as broad as saving water, mobility and portability, engineering and medicine, time-saving technology. One of my favorites, it has some relevance in Hanover, New Hampshire during the winter term, improve the quality of life in winter. All right? Student projects have covered the entire spectrum. Some of them are shown here, very significant award-winning or well-developed projects over the past few years, students inventing a gyroscopic stabilization mechanism that does away with training wheels for children's bikes, to a therapeutic device for children in the developing world that don't have access to high-end physical therapy, a tissue stabilization device to aid in surgery, gastrointestinal surgery, to a very simple tray system developed, designed, engineered, and made out of just the right lightweight materials to reduce the incidence of carpal tunnel syndrome suffered by wait staff in fast food restaurants. All of these were student ideas, student projects that are being pursued well beyond the end of the class. This class is taught in a learning environment that's a true peer learning environment, a true fully flipped and coached classroom. This is the studio where this and many other project-based courses are taught, the Couch Engineering Design Labs. You see here late in the term an accumulation of students in the class working on their projects, and to a point that was made earlier about this relentless pressure to drive down student-faculty ratios not necessarily being in the best interests of our students or their education. This is a class that works best with 50 to 60 students in the class, broken in teams of 4, enabling us to assemble talents according to interest, expertise, technical background, and really put together a powerful group working on solving an important problem. You see students running around in this picture. What you also see is the instructor hiding in the back. This is John Collier, who is one of the Gordon Award recipients this year, wandering through, checking on every student's progress. We also have professional staff, PhDs and master's level machinists, engineers, someone who's got expertise in fluids and materials, walking through the classroom, acting as secondary instructors, helping guide the students. And we also use senior students who've been through their course as advanced TAs just to poke, prod, ask questions, make this very much a student-centered peer learning environment. It's these elements that have contributed to this rich experience that students undergo. I meet students who are out a decade or two in my travels as dean of the engineering school who point to this class as what fundamentally cemented their interest in being an engineering major, their interest in being a technology leader. This ethos plays its way all the way through our undergraduate curriculum in other interdisciplinary courses of engineering. One example is a structural engineering course, structural analysis, taught by Professor Vicki May, where the students undertake a challenge that's posed by the local community. Here was a case where the local community said, in one case, a women's shelter, we'd like to have a picnic area and bench that everyone could sit on and gather outside. Another, the local community saying we'd really love to have a tree house for children to play on public land in town. The students undertake this design challenge. They don't have to be civil, mechanical, or structural engineers to undertake the class, but they are divided into teams, each team having responsibility for a specific part of the design and structure. But what changes this compared to other classes is these elements all then need to integrate with one another smoothly and seamlessly to develop a good for the public environment. And so the challenge and pressure that these students feel in integrating these different elements of design and construction is enormous, and it's enabled them to do incredible things. Another example is a course in advanced computer-aided design taken by senior undergraduate students. Again, the hands-on, entrepreneurial, open-ended nature of the course. The first half, the first 6 weeks, students are doing standard problems, doing analysis, working on some small projects. The last 4 weeks of the term, the professor finds a different, simple mechanical device, generally one that has wheels involved, and there's a reason for that, walks into the class and literally puts a stack of patents on the desk and says to the students, here is the existing patent literature covering this class of devices. Your challenge in the final 4 weeks of the term is to read through this, come up with a design, innovate, that goes beyond the boundaries of the existing patent coverage, design, build, and test the device, and then here's where the wheels part comes into play. We're going to have a very public relay race which started in our engineering building, has now become something that's outdoors on the campus as a public event for the students to show off their engineering skills, their teamwork, and their design creativity. What this does is help make engineering seem accessible, engaging, creative, and fun to the rest of the campus. And it's another one of these events, another one of these courses that really challenges our students to think creatively and think like entrepreneurs. All right. Yes, here's an example of the outdoor race. Here's an example where they're off and running. And I think I deleted one other slide that I had, but showed you where accidents happen. And actually, that's an important part of the engineering design process that we want our students to learn. Our undergraduate programs that form part of this collective engineering entrepreneurship program happen in the capstone design course in the student's 5th year. Because again, I remind you, we are a 5-year, fully integrated undergraduate engineering program. Here we do what many of you do, what many of us do. We solicit project ideas from local industry. Some financial support is provided. We bring them in, student teams are assembled, and their task is to develop a design for the industrial sponsor. What's different about this is this class is not segregated in any way according to engineering discipline. There are no mechanical engineering projects, there are no chemical engineering projects, there are simply projects that have a desired outcome. Every student in the class takes this course, and the instructor decides which project needs 2 chemical, 1 biomedical, and electrical engineer working as teammates to try and advance the solution. Another aspect of this course that's fairly unusual for us is that over the past 3 years, over 85% of the project submissions and over 80% of the selections have come from nonprofits or startups or very small businesses. And by very small businesses, I mean businesses that employ 100 individuals or less. These are incredibly rich projects that challenge our students to function as interdisciplinary entrepreneurial design leaders. There is so much that's open-ended, so much that's not clearly defined when a project comes from an individual entrepreneur. But the students have gotten a very rich experience undertaking these classes, and in fact, their projects have been entered in competitions such as the Collegiate Inventors Competition or the BME START competition for biomedical engineering projects. They've been finalists for the past 5 years, and they've also received 2 first-place awards in this time frame for their designs. The interdisciplinarity, the open-endedness, and the selection from very small entrepreneurial startups, while it doesn't do wonders for us financially, is a wonderful place for the students to challenge themselves and challenge and develop their engineering skills. So let me shift gears a bit now and speak about our engineering entrepreneurship program element that happens at the master's level. The second element, the master's level program that Dan mentioned earlier in his introduction, is the Master of Engineering Management, or MEM program. This is a program, as I said earlier, that my colleague Charles Hutchinson was instrumental in getting off the ground. This is a program that's designed to prepare BS engineering students for engineering leadership and management in a corporate environment. It was created in 1989 and developed through the 1990s as a professional project-based master's program in partnership with our business school at Dartmouth, the Tuck School of Business. The curriculum draws from both. The curriculum challenged the students not just in the classroom, but to do project work. The curriculum provides elements that are focused concentrations in areas such as entrepreneurship, healthcare, energy, trying to get them to orient their engineering and business careers in directions that align with the major themes that emerge from the grand challenges in engineering. And we certainly encourage our students to enter their work in business entrepreneur competitions. One of the unusual elements of this particular program is a course that's required of all students in data-centered technology assessment. The students are presented here as well with a very open-ended challenge. It's a structured approach to assessing technology readiness. They're asked to think about themselves as the leader of a corporation. They're asked to think about whether or not, if they were the CEO, would they invest in a particular technology, or should they be choosing alternatives? To do this, there's a multi-step process where, of course, they have to understand the problem first, search for competing and complementary technology, cost, performance, engineering design, environmental criteria need to be assessed. They consult experts with phone calls, reading the literature, reaching out with visits, do an economic analysis, a detailed technology readiness review. One of the things that we ask of them as well, which is a real challenge for any of you who work in the private sector, is to anticipate and assess the regulatory environment. What regulations are in place now that might impact your decision to implement this technology? What regulations might be in place 5 years or 10 years from now? And how does that affect the business case? How does that affect your investment in developing this technology? Regulations that might limit carbon emissions are a perfect example that provide a very challenging framework for them to think about this technology development approach. You see some example programs listed here, or problems listed here at the bottom. They're not all in the energy space, but significantly they are, because these and biomedical problems pose some of the most interesting challenges. Students going through this have been extraordinarily successful in some of their work, in business plan competitions, in case competitions, and in representing their ability to bridge the gap, bridge the divide between engineering and business, to be engineers who can pose and develop and lead credible technology-based solutions. The third element in our engineering entrepreneurship program at Dartmouth focuses on the PhD, the doctoral level element designed to develop, or focusing on development of what we call the Engineering PhD Innovation Program. Now, before I wrap up by speaking about some of the elements of this program, I'd like to step back and talk about the national context in this area in particular. If we take a look at doctoral level enrollments and doctoral degrees, these are PhDs in engineering that have been granted over the past 10 years. On the top of the slide, you see fairly significant growth in PhD engineering enrollments. In fact, it's grown 25% over the past 5 years alone, based on data reported by ASEE. If you look at growth in the number of engineering PhD degrees granted, there's been 19% growth, so not quite at the same level, but significant growth over the same 5-year period. And if you look closely, you'll see there was even more significant growth in PhDs being granted from 2003 to 2008. Where do these PhDs go? Well, what I'm showing you here are data from a very recently published NSF report. This year's Science and Engineering Indicators came out just a few weeks ago that looked at employed U.S.-educated PhDs in a range of fields. You have the life sciences shown here, physical sciences, and then also engineering. 1993, 2003, 2013, you can see that growth in engineering PhD employment was greater than 30% each decade. So we're producing more PhDs, but it certainly seems as though the marketplace is able to absorb them. But where specifically are they going? Right? Well, if we look at academic employment of PhD engineering graduates compared to life sciences and the physical sciences over the past 3-decade period, and here it's defined as the percent employed by 4-year universities, so many of these are tenure-track faculty positions, many are also research and research staff positions. We see in engineering, while there was absolute growth in the number, it was far less than the overall level of engineering employment, so the percentage was declining, to the point where now only 1 in 4 engineering PhDs are employed in academia. 1 in 4. Think about that. They're not all professors, and 1 in 4 of them are employed in academia. Let's look at the academic opportunity a little bit more closely. These are data from ASEE. Look at 2008, 2013 for different indicators and the percent change. So if we look at the number of PhD graduates between 2008 and 2013, we see that 18.5% growth that I alluded to earlier. If we look at the number of tenure-track faculty in U.S. educational institutions, this includes computer science where it's within engineering. It does not include computer science where it's outside of engineering. We see 5.9% growth in the number of tenure-track faculty. If we look at growth at the assistant professor level, we see a growth of a grand total of 59 positions nationwide over this 5-year period. And so doing a quick analysis, thinking about tenure denials and early promotions to associate, it's not hard to come up with an estimate of the number of annual assistant professor openings, and that's between 950 and 1,000 a year. So we're producing 10,000 engineering graduates, PhD graduates a year, with 950 to 1,000 tenure-track assistant professor openings in engineering in the United States available each year. So let's think about our programs for a minute. In the US, we have engineering PhD programs built on the model of the sciences that work exceptionally well to train researchers who are deeply versed in a particular area of technology. They learn fundamentals in the discipline. They pass a comprehensive qualifying exam. They take additional coursework or seminar study to support their research project, and they do and undertake deep exploration of an original research question. In our programs, we pay very little attention to doing more than training them as researchers, teaching them to take the courses that support the underlying technology that they're trying to develop, the underlying engineering science problem they're trying to unravel. Very few of us teach them how to become good and effective engineering teachers. Very few of us think carefully and deeply about helping provide the breadth plus depth that's often valued by industry. And what about the educational elements of entrepreneurship? Many universities have centers that allow students to take their technologies, gain some mentorship, and try and move forward with an idea. But often we pose a choice. Do you continue your studies, or do you take time off to try and develop this potentially commercializable technology? What about building educational elements of entrepreneurship into the program for some of our students? Our data suggests that at most, 1 in 4 of our engineering PhDs work in universities, 1 in 10 will obtain tenure-track academic positions. And if you think about the number who can become faculty at 108 of the Carnegie Foundation very high research activity institutions, it's certainly less than 1 in 10. So the question I will pose is, do we have a system of PhD education in engineering that is driven and structured primarily to produce deeply talented, outstanding researchers who not exclusively but significantly are being trained to take research positions in the academy when that is not anywhere near where the vast majority of them go? So with that as context and with that as background, this was the motivation for our development of the final element of our engineering entrepreneurship programs, the PhD Innovation Program, which we at Dartmouth launched in 2008. This program was designed from the beginning to be small and selective and focused. We limited admission to 5 students per year, and we've maintained that throughout the 6 years of the program. These students undertake a different curriculum where they complement their engineering coursework by courses in understanding venture financing, patent law, organizational behavior and management, financial accounting, taught by colleagues in the business school, taught by faculty who have entrepreneurial experience on our faculty. We have developed funding to provide reverse fellowships for these students. And so they are not supported by fellowship support at the beginning of their PhD studies. They are supported by fellowship support at the end of their PhD studies. The idea being that they enter a program, develop their bench scale skills, begin to work on a technology with their advisor, and 2.5 years in, when they've built their fundamental skills, maybe written a master's thesis, see a direction that might be orthogonal to the NIH grant that was funding their work. Fellowship funding kicks in to enable the student and his or her advisor to take that in a very different direction. We've had broad faculty participation. There was an interesting faculty conversation around the start of this program, as you might imagine. Is this reducing the amount of technical work students will develop in the PhD? Will they still work deeply on an engineering research problem? 5 years in, we've had more than 1/4 of our faculty engage in advising students in this program, and over the past 2 years, we've seen this program begin to get some external recognition for providing a very different and alternative path for engineering PhDs. If we look at the outcomes for students who've gone through this program compared to our baseline PhD program, admitting that the numbers are small because the program is only 5 years old, but the outcomes are dramatically different. This first chart, I'm showing you the number of PhD students as a percentage who have filed for intellectual property protection on something that they developed in their PhD program for students in our core existing PhD program versus students in the PhD innovation program. You see a factor of 3 difference. Students in the PhD innovation program are 3 times more likely to be focused on orienting their research towards developing something that is commercially viable and has possibilities beyond the university. If we look at next steps after they earn their PhD and look at the percentage who undertake postdocs versus the percentage who undertake postdocs in each program, you see a dramatic difference. Nearly 40% of our PhD graduates undertake postdocs as their first position after earning their PhD. I suspect that's typical of many of us in this room. If you look at those from the innovation program, it's fewer than 1 in 6. And if you look at employment, the number of students who either establish their own company or join a technology startup in a leadership position, this is the most dramatic comparison of all. 5% of our students were going down this path before we created this program. It's now over 70% of our students in this program who have chosen to head in this direction after earning their PhD. So for this collection of programs, for an integrated pathway in engineering innovation from undergraduate through the doctorate to prepare students for engineering leadership, we were pleased and proud to host the group from NAE on our campus in May and be named as this year's recipients of the Bernard M. Gordon Prize. Now, what I've ended here is by speaking about experiments in engineering PhD education and a particular approach that we've taken and I've asked you to think about in a broader context. We are certainly not the only ones who are undertaking experiments in engineering PhD education. MIT has recently launched a PhD in chemical engineering practice designed to produce PhD graduates who are prepared to assume leadership positions in industry soon after graduation. Duke has established an innovative PhD Plus program where their PhD students have opportunity for additional coursework, additional project opportunity, additional learning outside of the regular structure of the PhD program to build on this. Stanford, certainly through their biodesign program, where they take fellows from across the country and have them interrupt their PhD studies for a year to work on technology development in the biospace in an area they care about, is an important example. And even overseas, we see a collaboration between Trinity College Dublin, University College Dublin, and Queen's University. They've started a few years ago something they call the Innovation Academy with many of these same goals. There are certainly other programs. This is not meant to be a comprehensive list, but I will argue that the list does not seem to be very long. If we think about outcomes for PhD students and we think about engineering pathways, shouldn't there be more opportunities for students to think about their PhD in this broadened way, not directed necessarily towards an academic tenure track position? So let me close by simply going back to the beginning and talking about the national imperative that motivated a lot of our work and has motivated a lot of this discussion. What I'm showing you here is a Boston Consultant Group ranking of the top 10 innovation nations from their report, which was issued in 2009. This looked at a broad range of criteria, laws, financing, level of technology development, infrastructure to support innovation and technologically creative businesses. If you look at the top 10 nations, the good news is the United States is on the top 10 list. It was number 8 in this list. Other innovation rankings coming from other groups, other consulting groups have had the U.S. positioned differently, but generally in the same range and always in the top 10. But I've plotted that against the number of bachelor's levels engineers graduating in each of these innovative economies as a percentage of the national population. You don't have to look hard to see where, well, now you can't look at all, where the U.S. stacks up relative to the others, right? This is in 2006. We were at best a factor of 1.5 below Switzerland, and you can see how we compare to many of the other nations on this list. Now, over the past decade, and particularly over the past 5 years, there has been a tremendous response to this challenge, this need to help develop a larger amount of engineering talent to be global competitors on the innovation, on the technology development stage. Here I'm showing you full-time undergraduate enrollments in engineering for the period 2003 to 2013, and you can see the percentage growth over each of those 5-year periods. If we look at the number of bachelor's degrees that have been granted, we've seen a significant increase here as well. And in fact, if you project forward from these enrollment numbers, I'm predicting that once the data from 2014 are accumulated later this year, we will find that we produce between 95,000 and 100,000 engineering bachelor's degrees in this country, and next year, 2015, we will graduate more than 105,000 bachelor's degrees in engineering for the first time in this country. This is remarkable, considering where we were 5 and 10 years ago when Rising Above the Gathering Storm, the Council on Competitiveness report on innovation, Innovate America, and other reports looking at engineering education were first written. This is absolutely remarkable. But we step back and ask ourselves, if our broad goal is to create technology leadership, to create the next generation of technology leaders who can understand and create and lead the innovation and commercialization process, we need to think about this very deliberately in our engineering educational programs, and I will argue even in our PhD level programs. Can we create a leader out of absolutely every student who walks through our doors? Perhaps not. I think most of us know the answer is probably not. But what we can do is provide opportunity. What we can do is inspire our students to think about being leaders, to identify and nurture talent and latent interests and abilities, and prepare them for opportunity, recognizing that for some of them, the opportunity to be a leader, to be a technology leader, is not going to come until 5 or 10 or 15 or 20 years after they leave our hallways. Our current BS enrollments, which were unthinkable 5 years ago, give us tremendous opportunity. Growth occurring at the PhD level also gives us tremendous opportunity as a nation. The questions we have, the questions we all have, are first, will we have the research funding and infrastructure to support their scholarly work? And I think equally important for all of us in this room, do we have the right programs in place to educate them, not just to be researchers, but to be technology leaders? So let me close by simply commenting on something that Dan said earlier in his remarks. Dan asked us all to think ahead as to whether or not we need to own the engineering discussion, whether we need to own the E word. Well, from my perspective standing here to all of you, I think the answer is an emphatic yes. Look at those videos that we saw earlier today. How could you not be inspired? How could a prospective student not be inspired by looking at that? What I tell our students when they come to ask about engineering and whether or not it's for them, particularly being at a liberal arts university, is I ask them what they care about and say to them, if you don't like the world as it is, then change it. And engineering is the best set of tools, the best approach, the absolute best way for you to develop the skills and knowledge to have that impact, to make a difference, to change the world. That's the challenge for all of us. So thank you, Dan. Thank you, NAE. Thank you for giving me the opportunity to speak about our programs this afternoon. I do if you do.
Yeah, well, we have it's in the program, it's all right. We have a time for a couple of questions. If anybody would like to ask a question, I won't ask a question about what I'm supposed to do with the other $499,500. I always thought you were going to give that back to the Academy. I'm sorry.
That would be a really nice gesture, wouldn't it? But
No,
but
no. I won't go that far. But someone must have a serious question, and I see a hand, and a microphone is coming towards the hand, or a hand or two.
Thank you. Have you done any correlation between students that come in your program and their prior undergraduate experience? I mean, we're seeing emergence of the first robotics program, the maker movement, and so forth. Are you seeing that that's having any impact on the input to your program?
So we've looked at students who come into our engineering management program in terms of their background and experience. And they all have engineering degrees, but we do look very carefully to see some of them have tried something, whether they've tried something creative or entrepreneurial in their undergraduate background that makes them a great candidate for this program. I may have had a bullet on a slide, I didn't mention it, but 15 years out, we find that between 20 to 40% of them have started their own enterprise at some point in time. Clearly there, we're picking students who have a predisposition. We help provide the framework to enhance and build on that, and that launches them off in that particular direction. In the PhD program, we are taking in PhD students who are finding us because they are interested in our PhD research, and they see this as an interesting additional opportunity. So those students are no different as a cohort than any other sets of students that would apply to a PhD program. Now, your question about FIRST touches very directly on the undergraduate question, and I'll give you two answers to that. Number one is I don't know for us because we don't track it. Number two is I'm doing some work for the state of New Hampshire, and Dean Kamen, who's the founder of DECA and founder of FIRST, is on that as well. And they are undergoing multi-year studies with Brandeis and a few other universities working with them to ask exactly that question. How does participation in FIRST translate to subsequent engagement in and then persistence through engineering? Those reports aren't finalized, so I don't have the answer to you, but that's exactly the right question to be asked. And I think within 6 months to a year, they expect to have that published.
May I ask one question? Joe, what do you think would be the largest number of PhD students you could have in this innovation program relative to the size of your faculty? What should we think about in terms of scale here?
I'd like to see, so we've talked about that a lot, Dan, more in terms of a percentage of our student body, and I think the right carrying capacity is about 25% of our PhD student body, maybe a little bit more, but that feels about right. What that does is take our faculty who are focused in this area, and that's not everyone, right? A quarter of our faculty have started a company in the past decade. They tend to be the ones who gravitate to this program, to advising students in this program, but there's a larger number who are also interested and engaged. I would say 50% of the faculty, 25% of the PhD students is probably about the natural limit of this.
Good. Thanks very much. Oh, there's a question. We have a mic here, third row, back, your left.
Thank you, Louis Branscombe. How much a response are you getting out of the private sector for this trend in engineering education, particularly at the upper levels? It strikes me, I used to be at IBM, and one of the things I was responsible for is IBM's contributions into universities. We were contributing to research. We weren't doing what you're describing.
Right.
But I've recently predicted that industry must, given the trend in the future, must get more involved in supporting this kind of trend in the universities. Is it happening?
So at the undergraduate level, obviously there's engagement, but if you're speaking particularly to the MEM program, yes. The PhD program, let me simply say that's developing, so we're not at that point. We've had conversations with a few major corporations, IBM in particular, who are very interested in the skills that this helps students develop and how that fits into their broad notion of systems engineering, systems thinkers, T-shaped individuals. And so we are continuing to explore that opportunity, but right now there is no particular partnership with any major corporation. But they are hiring our graduates, the 30% who are not going off and starting their own company or joining a startup. Those other 30% are going to Microsoft, IBM, GE, places like that.
Well, I think we better maybe hold the questions to the break. We'll have a break in a few minutes, and Joe is not going anywhere, I'm quite sure. So you'll be able to talk to him. But just before the break, we want to show two videos. Then we'll have a break for half an hour, and I think you can follow up with lots of questions then, if that's okay.
That's okay.
Thanks. Thank you, Joe, for first of all, for winning the prize to begin with, and a really excellent presentation for all of us.